Good morning. I'm a PhD student of the University of Brescia in Italy, and I will present a work realized in collaboration with the Fondazione Bruno Kessler of Trento in Italy. This work, as well as my PhD project, is focused on the integration of acting, planning, and learning, particularly on the online learning of planning domains from sensor data. Firstly, we will give a brief introduction and motivations behind this work. Then, we will talk about an already existing framework called Plan, Act, Learn, by defining the problem, a possible resolution approach, and an implementation algorithm. Finally, some experimental results are reported and conclusions are given, as well as future works and in-progress ones. Symbolic planning techniques are based on abstract and most often discrete representations of the world where agents operate, usually called planning domains. A good planning domain should be simple enough to make automatic planning feasible, as well as detailed enough to generate effective solution plans. A good planning domain should also abstract away the details of the world state which are irrelevant for the achievement of the agent's goals. However, since the specification of a planning domain is a challenging task, in many real applications it may happen that agents don't have a good planning domain in advance. For instance, a robot moving packages among rooms in a building could have a model of the map of the building with some flaws or relevant missing details. In these cases, agents should be able to learn and update their models while acting in the world and observing the consequences of their actions. Let's clearly define what are the planning domains in which we focus in this work. They are discrete and deterministic planning domains. A discrete planning domain is represented by a finite set of states, a finite set of actions, and a transition relation, while a discrete and deterministic planning domain is a discrete planning domain where the transition relation is deterministic. Generally, a planning domain can be represented in an explicit way, for example, through an automaton which contains states and transitions from states to states caused by actions, or in an intentional way, for example, through an action model, where each action is specified by its name, parameters, preconditions, and effects. The intentional representation is much more scalable with respect to the extensional one, since we don't have to explicitly enumerating all possible states and transitions. The PAL framework has been introduced by Serafini and Traverso in 2019. My PhD project builds upon this already existing framework. Particularly, the framework aims to learn an extensional representation of a discrete and deterministic planning domain from observations in a continuous space navigated by the agent actions. This is achieved through the use of a perception function providing the likelihood of a real value perception being in a given state of the planning domain. The agent chooses its actions in order to accomplishing its task. Then, by executing them and observing their effects, it online learns an extensional representation of the planning domain and a perception function. Hence, the PAL problem consists in learning an extensional model and a perception function such that, given a perception goal set, the extensional model has a plan to reach a goal state. The environment where agents operate is formalized as a non-deterministic and infinite state transition system. The learner perceives the environment through a series of continuous variables called perception variables. Notice that the agent doesn't know the environment. Its only knowledge about it is the one provided by the perception variables after executing actions. The agent also learns an extensional model. In this framework, the extensional model is formalized as a deterministic and finite state transition system. The learner incrementally constructs the extensional model by explicitly storing visited states and executed transitions. In order to learn the extensional model, a random exploration strategy can be applied. However, it doesn't scale up to large state spaces. Alternatively, the agent could use some prior belief about the environment. And following this idea, in this work, it's supposed that this prior belief is expressed through an exploration model, that is, a planning domain specified in a planning domain definition language, for instance, PDDL. The PDDL state represents the current belief of the agent about the status of the environment. Moreover, in this work, it's not required, the exploration model is not required to be fully correct. Indeed, the learner revises the exploration model whenever a failure occurs in the attempt of executing an action. Intuitively, the learner will decide which actions to perform by computing a plan that reach a goal state. The agent also learns a perception model, that is the perception function. Intuitively, the perception function discretizes the infinite set of continuous environment states into the finite set of extensional model abstract states. Each state, the learner updates the perception model using the perceptions from the environment. And each state in the perception model is represented by a probability density function. A concrete but still very general model which we decided to adopt in this work for a single variable perception function is the normal distribution. Hence, each state of the perception model is a Gaussian mixture, where one normal distribution for each perception variable. The parameters of the distribution can be learned online, given a sequence of observations associated to the same state. Firstly, a plan is searched for by the extensional planner. However, the search of such a plan may fail because the transition function known by the agent may not yet be complete enough. And if no plan is found, a goal-driven exploration strategy is applied by means of an exploration planner. After that, the first action of the plan is executed, and so on. So let's take an insight on how the algorithm works. Initially, the agent perceives its continuous environment state. Then, it tries to map the perception in one perception model state. If the likelihood of observing the perception being in each of the perception model states is lower than a given threshold, then the agent creates a new state in both perception and extensional models. Otherwise, it selects the maximum likelihood state as the next one. And if the destination state is a goal one, then the algorithm stops and returns success. Otherwise, the agent checks if the last executed action has failed, and in such case, it revises the exploration model. The exploration model is revised by constraint on the grounding of operators in such a way that only actions which are not previously failed can be generated. In this work, it is assumed that an action execution failure occurs if the agent doesn't change state after executing an action. After that, a plan is computed with extension and exploration model, the first action of the plan is executed, the learner, the agent, again perceives the environment, and so on. If a goal state is not reached within a given time limit, then the algorithm stops and returns failure. The proposed approach has been tested in 3 well-known planning domains with about 100 benchmark instances taken from past international planning competitions. Here we present 2 settings, repeat and continue. In the repeat setting, the PAL algorithm is repeatedly run with the same initial state and goal. We call each of these runs an episode. While in the continue setting, the goal changes among episodes, and the initial state is the last visited one during the previous episode. Since the exploration model is an approximation of the real world, it may happen that an action contained in a plan computed by the exploration planner cannot be executed in the real world. So in this experimental analysis, I've also evaluated the capability of the learner to correctly revise the exploration model whenever a failure occurs in the attempt of executing an action. This figure shows the average number of failures with both settings, repeat and continue, for 10 episodes of logistics domain. For the repeat setting, the number of failures is 0 after the 5th episode and tends to decrease. Remarkably, even for the continue setting, the number of failures tends to decrease and is close to 0 after few episodes. This is because the number of not executable actions is incrementally learned starting from the first episode, which reduces the possibility of action execution failures among episodes. Similar results have been obtained for other domains. So I've presented a novel algorithm to learn an extensional representation of a discrete and deterministic planning domain and a perception function. The algorithm interleaves planning on both extensional and exploration model. Moreover, it refines in an effective way a potentially incorrect exploration model. And finally, by providing the agent with some prior belief about the environment, we have significantly improved the scalability of the previous work. Indeed, problem instances solved in this work cannot be solved by previous one without a goal-driven exploration strategy. And moreover, the extensional model learned with an exploration model is more effective since it contains states and transitions which are relevant for the agent typical tasks. Future works are focused on dealing with more complex and noisy inputs. For example, by providing the agent with an RGB camera instead of just using GPS and RFID sensors, and exploiting neural networks to process the perceptions, for example, object detectors or scene classifiers. Other future works are focused on the learned representation of the planning domain. As we have said before, the intentional model is much more scalable with respect to the extensional one. So instead of explicitly enumerating all visited states and executed transitions, we would rather learn an intentional representation of the transition function, for example, an action model. We have already submitted a conference paper on this topic. Other future works are focused on the perception clustering, which we would like to be with probabilistic and incremental approaches. So, for example, incremental versions of the expectation maximization algorithm, since in this work we are using Gaussian mixtures. Finally, and probably the most important thing, is learning the abstract state structure. So we would like to find a mapping among perception variables and state variables, continuous perception variables and discrete state variables. For example, in the presented work, all perception variables are mapped into one single state variable, that is the state identifier. However, this state variable is meaningless. We would rather have a mapping into meaningful state variables. For example, objects and properties among these objects. And this is the research plan timeline of my PhD proposal. Thanks for your attention.